Back in the tutorial for the properties of alcohols, I mentioned that alcohols can be primary, secondary, or tertiary in structure, depending on where that OH is. And I said that they would have an impact on the chemistry. And this is really important because when we get to oxidation, whether it's a primary, secondary, or tertiary alcohol, it's really important when it comes to oxidizing them. All right, so we're going to look at the oxidation of primary alcohols in particular in this tutorial. Secondary and tertiary, I'm going to deal with in another one. So what happens when we oxidize a primary alcohol? So if we take our primary alcohol, if we oxidize it slightly, we end up with something called an aldehyde. If we oxidize that further, we end up with something called a carboxylic acid. So what do they actually look like? So our primary alcohol looks like this. We start with an R group. It can be any length carbon chain, but the most important thing is on the end carbon, we've got that OH group. Now its primary official explanation is because it's bonded to a carbon that's bonded to two hydrogens. As you can see clearly here, that OH is bonded to a carbon that's got two hydrogens bonded to it. Now, if we oxidize that primary alcohol, the O in square brackets represents oxidation, then we end up with the aldehyde. You can see an aldehyde is essentially a C double bond O and a H on that end carbon. Okay, so what we've essentially done is remove a couple of hydrogens from that alcohol, and we've ended up with a double bond on the oxygen and just a single hydrogen. Now, that is an aldehyde group. But if we oxidize that further again, and if we use that symbol of O in square brackets, we end up with a carboxylic acid. So again, the same R chain, but this time the end carbon still has that double bond O, but this time we've got an OH as well. Okay, so comparing it to the aldehyde, we've added an oxygen there. Okay. So you can see how in old money, if you remember oxidation, it's either the removal of hydrogen or the addition of oxygen. That's what we're talking about here, okay? So we can go from primary alcohol to aldehyde and then oxidize it further to a carboxylic acid. Now we can stop that process halfway, or we can allow it to go all the way through to a carboxylic acid. Now I'm going to talk to you about how we do that in a second. But first of all, we need to know what our reagents are. How the hell are we going to oxidize it? What are we adding to this alcohol and or aldehyde to actually oxidize them to a different functional group? So of course, what we need to do that is an oxidizing agent. Now we have a choice of two here. There are two main oxidizing agents that we use in A-level chemistry. The first one, bit of a mouthful, acidified potassium manganate 7. That's 7 in Roman numerals. That basically represents the oxidation state of the manganese in there, and I'll show you that in a second. That can be shortened or, basically condensed down to H+, that's our acidified bit, / KMnO4. That is our formula for potassium manganate 7. Or we can say H+, MnO4-, which is the same thing. It's just that we're not using the potassium doesn't get involved. So we can just use the MnO4- ion, as short for our acidified potassium manganate 7. Okay, so you can use either of those in an equation. I tend to use the two ions, H+, MnO4-, but that is our shorthand version for that oxidizing agent. So as this oxidizing agent is actually oxidizing our alcohol or our aldehyde up to a carboxylic acid, we do get changes. That MnO4- gets turned into Mn2+ during the reaction. So we can see here, of course, with it being an oxidizing agent, it gets reduced itself. So it's going from a +7 oxidation state to a +2 oxidation state. So it itself is getting reduced whilst it's oxidizing our primary alcohol or our aldehyde. And that brings with it a really useful color change. Our potassium manganate 7, our MnO4- is actually purple in color, quite a deep purple. And when that gets reduced, it actually turns colorless. Mn2+ is colorless. So whilst you're using this and you heat it with your primary alcohol, the alcohol will get oxidized and it will turn from purple to colorless as the manganate is reduced. Okay, so it's the change in oxidation state of the manganese that causes the color change during this reaction. And we can see that there's oxidation actually happened because, of course, if there's no oxidation, you don't get a color change, because if there's no oxidation, there's no reduction of the manganese. So that's our first option. Okay, our second option is very similar. Our second option is acidified potassium dichromate. Now, acidified potassium dichromate, again, we need our H+. And that's with K2Cr2O7. That's our full formula for potassium dichromate. Of course, we can just use the ion. Potassium doesn't get involved. So again, I tend to use the H plus Cr2O7 2 minus. Just, that's the shorthand for it. And again, because it's an oxidizing agent, it gets reduced during that process. So our Cr2O7 2 minus, that gets reduced to 2 lots of Cr3+. I've put 2 there because obviously there's 2 chromium atoms in our Cr2O7 2 minus. So you can see that the +6 oxidation state of the chromium in the dichromate actually gets reduced to +3. So again, we've got a reduction in that reagent whilst it's oxidizing our alcohol or our aldehyde. And again, it brings with it a very handy color change. This time, our dichromate is orange in color. And whilst we heat that with our alcohol, as the alcohol gets oxidized, this gets reduced. And as it gets reduced, it turns to green. All right, so orange to green. For some reason, I have a traffic light in my head, as it goes from red to orange or amber to green. Okay, so that is the change when you're using dichromate. And in fact, this dichromate one is the one we tend to use. If you used the potassium manganate, it would work in exactly the same way. But we do tend to use the dichromate because it's a bit of a weaker oxidizing agent. It's not so strong, okay? So if we, just want to go to the aldehyde, if we're only going to go halfway in terms of oxidation, then we use the weaker oxidizing agent and we stand more chance of actually getting the aldehyde. Speaking of which, what if we don't want to go from here all the way to here? We need to stop this process. If I heat an alcohol with one of these two in a test tube and just let it run, it will get oxidized to the aldehyde and then get further oxidized to the carboxylic acid. So we need to think of a way, because we can isolate this. We need to be able to stop this halfway through. We need to just oxidize it a little bit to get the aldehyde and then somehow remove that before it gets turned into a carboxylic acid. Well, it is possible. So there are 2 different methods, depending on whether you want the aldehyde from the primary alcohol or the carboxylic acid. So we'll start by looking at how we're going to get from a primary alcohol to our aldehyde. So the equation for this is as follows. We take our alcohol. Again, it's a primary alcohol bonded to a carbon with 2 hydrogens attached to it. Then we add this O in square brackets, and that represents the oxidizing agent. So the oxygen is supplied by the oxidizing agent. We then get our aldehyde, which is our R C bond O H. And of course, we get water as a byproduct. If we're looking at these molecules, as I say before, we're removing, let's say, this hydrogen up here and this hydrogen on the alcohol group. So if we take those 2 away, a double bond forms here with the oxygen and we get a single hydrogen. So we're releasing 2 hydrogen atoms here. This oxygen from the oxidizing agent bonds with those 2 hydrogens to make water. Okay, so this is the overall equation for the oxidation of an alcohol to an aldehyde with 1 oxygen in square brackets here. So this oxygen in square brackets, as I mentioned, supplied by the oxidizing agent. Now, I said we need to actually remove this aldehyde from the mixture before it gets further oxidized to the carboxylic acid, which will very, very easily happen. There is one particular thing that we need to use here, and that is distillation. So we need to heat this primary alcohol with the oxidizing agent with distillation. So as that aldehyde is produced, it actually evaporates and goes into the condensing chamber, and we can take it out of that reaction mixture before it ends up getting further oxidized to the carboxylic acid. If you want to know more about distillation or you don't know much about the distillation process, I'm going to use this as an example in the distillation video in the practical section. So if you want to know more about that, check out the distillation video. But this is more about the equation, okay? So primary alcohol plus 1O in square brackets gives us aldehyde and water. So what if we don't want the aldehyde? What if we want to take that primary alcohol and just, convert it all the way straight through an aldehyde to a carboxylic acid? Well, the equation is this. So we start with our primary alcohol. This time we need to oxidize it further. So we're using 2 oxygens in square brackets from our oxidizing agent, and then that will actually produce our carboxylic acid. So you can see here we've got an extra oxygen in there now and water as a byproduct. So this here, okay, we are losing 2 hydrogens, okay, still, but this time, okay, we're adding an oxygen in as well, okay, so 2 oxygens here forming our carboxylic acid and water. So we don't have to stop this process. This carboxylic acid cannot be oxidized any further. So we don't necessarily need to use distillation to remove that product as it's made. So rather than distillation, we use a process called reflux. Now again, if you want to know more about the reflux process itself, then take a look at the video in the practical section. So important things to note here. We can go through an aldehyde to a carboxylic acid from a primary alcohol. We have a choice of 2 oxidizing agents. Know both of these, but this one, the acidified potassium dichromate, is the one we tend to use for this process because it's a not so vigorous and oxidizing agent. These color changes massively important because not only do you use these to oxidize to create different functional groups, they can be used as a bit of a test as well to see if you've got an alcohol present. Maybe it gets oxidized. Oh, you got the color change from orange to green or purple to colorless. Oh, something's being oxidized in there. Okay, so these can be used as tests as well. Your equations, massively important. They do ask for these in the exams. So primary alcohol to aldehyde, 1 oxygen in square brackets. Primary alcohol to carboxylic acid, 2, okay? And we get water as a byproduct. But the main thing here is, if you're going to stop this process halfway through, you need distillation. Remove that product because it's got a lower boiling point. It gets removed and you can isolate it. With this one, doesn't matter. You're going all the way to the end of the line here, okay? So you can reflux it, heat it and heat it and heat it, stop it when you feel like, and then you get your carboxylic acid out at the end. So the big dissociation here is heating with potassium dichromate, both the same, but this one you need distillation, this one you need reflux. So it's not different reagents you need, but a different process. So really important, this oxidation of alcohols, massive part of your exams, will always be in there in one form or another.